And let's begin. Hello, my name is Michael Boman. I'm a senior malware researcher at something called the Malware Research Institute. It's my 4th year here at 44Con, and it's about talk about why I'm here. Well, it's my 4th time here. I was talking about malware as a hobby. I talked about how to control your PC using Arduino. The last year I talked about looking at the malware analyzing as a big data problem using Hadoop and stuff. And this year I'll talk about malware reverse engineering. As I said, I call myself a malware researcher. I'm a founder of the Malware Research Institute. And it's quite fun, actually. I discovered that anyone can call themselves an institute. So I did. It does sound very good, right? Malware Research Institute. Well, it's actually quite funny. Oh, by the way, I have a big family. I have 6 kids, 1 more to go. So next year I have 7, and hopefully that will be the end of it. But I mean, the Nissan we're having is only a 9-seater, 8 passengers. So it's time to get a new driving license. So when I was started here talking about the malware research as a hobby, this was my malware research laboratory. It was housed under the stairs in my house. It was a motherboard, the bare essentials to make a computer, bolted to an IKEA Trufast furniture. There's not even a case for it. So that's where I started out. And it sort of worked until last summer when my hard drive decided to commit suicide, and I had to start over, and it was very, very heartbreaking for me because when I was talking at the 44Con last year, I just got the realization that I've lost over 6 terabytes of malware samples. So do I start over, or do I just call it quits? Well, I'm here now, so I started over. And I said, okay, let's buy some new hardware. So I got myself some new servers that's rack mounted, all secondhand. And I got myself a server rack, which actually is brand new. So now instead of having a Trufast IKEA furniture on my stairs, I now have an 18 rack units rack under my stairs. Oh, and I was using a lot of Amazon services. A lot. It's nothing in, I'm paying about 20 quid a month. So, not that much. So, to the topic. I'm going to talk about malware anti-reversing. And as a malware researcher, you get a lot of problem trying to figure out how what the malware is doing. They don't want to let you know. So I come across a couple of techniques. I've been reading a bunch of others. So this is just a recap of all the techniques I know about so far. This is towards a Windows x86 environment, so no Linux, no Macintosh, nothing like that. Just plain Windows, but that's what the malware likes. So it's either anti-reverse engineering or just silly stuff to take your time, because I mean I have a very, very limited time. I mean 6 kids. I have a day job. So, yeah. Let's go to technique number 1, breakpoints. I'm going to go through the, let's just skip ahead here. So the int3 breakpoint, it's the normal debugger breakpoint. If you're doing a breakpoint in a program that's using your all the debug or WinDebug or so on, this is what you're doing. And how it does it is that it replaces the instruction you want to break on with an int3, and once the debugger sees it, it's replacing it with the instruction you actually wanted to see and break on. So what the malware is doing, it's scanning itself for the opcode for int3. See if the memory I'm using is actually having a debug instruction. And if it finds it, it says, okay, I'm being debugged, let's behave nicely. After this, I will recap how to countermeasure it, if possible. Another way is to do a memory breakpoint, which means that the malware author is marking some memory as is page guard, which means that you get an exception once you hit it. Once you're trying to access the allocated memory, you're getting a page guard exception. So then the malware can have some code that says, oh, I got an exception, this is not expected, I'm being debugged. You also have hardware breakpoints. It's very similar to memory breakpoints. It's using different registers, works slightly different. It's unfortunately too complicated for me. I'm not that professional yet. So how to countermeasure this is one. Well, if the malware code is looking for int3 ops in its memory for see if it's being debugged, you just need to look if it's looking. Okay. For memory breakpoints, well, look for allocations that has the page guard option set. No biggie. For hardware, you can use the get thread context or get thread thread context to look to discover if it's any hardware breakpoints enabled. You can also use the SEH exception handling to discover them. Next technique though is timing techniques. It's many malware is having a sleep period where it's like you go and execute and then it waits a while before it's actually doing some bad stuff. And the whole idea is that during the analysis phases, your timer will run out before the malware is doing the bad stuff. Google has a famous 15-minute time frame. So if you don't do anything stupid or malicious in 15 minutes, it was okay. Google approved it. You just need to wait 16 minutes. So as a researcher, I want to cut this one down. So I'm changing my sleep call to just returns right away. The thing is that you can use something like RDTSC to count how many clock cycles has elapsed. You're doing a number of clock cycles. You do your extraction, you read the next value, and you calculate and see if the amount of time that passed is what you're expecting. So if you're saying you want to wait 5 minutes, you want to see 5 minutes of clock time passing by. You can also use the get tick count, get time of using get time, and numbers of timing functions to find out. So to contract this one, well, for the Win32 timing functions, you can always do a delay injection and just lie. You know, you do a delay injection to hook the sleep call, so it always returns 0. So it's always do a sleep 0, returns all directly, but you need to lie to the whole system that, yeah, it was actually 5 minutes that passed, or 1 day, or whatever. So don't forget that you need to lie to every single function. For the RDTC, you can actually mark it as a privileged instruction. So you load a driver that marks the RDTC as a privileged instruction, and then you can do your manipulation. But you have to remember to keep the timings correctly. You can't have the time of day say a different thing than how many seconds was it since boot up. So next part is the Windows internals. Am I going too fast? No? Okay, cool. So when you do you put a piece of code on the debugging, it marks in the system that the code is actually being debugged. And what you want to do as a malware author is to detect that you're being debugged, or as a malware researcher as myself, stop it from being detected that I'm actually looking at the code. So the process debug flags, you can actually use an undocumented class when you run it to the NtQuery process information, which means that when you are doing the NtQuery process, we call this the process debug flags, like this. It returns the reverse of debug inherit. So it's more complicated than calling is debug present. So of course, if it's false, then the debugger is there and you do no evil stuff. There's another one similar to that one, that you are having another debug object in NtQuery information process. And that one is a bit harder to manipulate. So that one is originating from the kernel itself. You also have a proper API that hides a thread from being debugged, which means you don't get any events from that thread to the debugger, including breakpoints. So an easy way is you create a thread using the thread hiding technique, and the debugger doesn't see it. What you need to do is intercept all the thread creation and make sure that that option is no longer present. This is one of those techniques, the Blockinput techniques. It's not really anti-reversing. It's just making you pissed. Because what it does is it's blocking all the inputs from mouse, from keyboard, and only the thread that called it can actually remove it. So basically, your computer stops working. Another easy way is to use the OutputDebugString. It's how you can get your program print F to the debugger. And what you can do, what you do as a malware author or someone who doesn't want to get reversed is you call it, and then you check if there are any error messages. No error messages, the bug is present. Simple enough. So how do we go about recovering this one on? I don't know. Can you see this? Because I can't. Well, the slides will be available both from 44con and from my own site. So NtQuery information, you look for the, you hook it, you lie about it. You filter out that option. When you're doing debug object handle, you just go and remove all the debug handles. Again, you're doing a DLL injection, and just make sure that you're acting as a rootkit to the malware. Again, same thing for the thread hiding. Scrub it away. Don't let that option be set. Blockinput, same thing. Make it a no op, or just step over. And hook the output debug string to always return an error. So it's not really that hard for Windows internals. No new drivers, it's just standard DLL injection. Process exploitation. That is a series of quite interesting techniques. If you start with the open process, it's when you are having a program under Debugger, it inherits the SC-debug privilege. So what the malware is doing is trying to open something like csrss.exe, which is a privileged process. You're not supposed to be able to attach to it. And if you get no errors, well, something's wrong, right? You're being debugged. This is quite debugger, what's it called? Dependent. Depending on if the debugger is doing the proper thing and reduces privileges, you're still having an issue opening other processes. But as standard, you're having privilege to attach to any process in the system. You can always check the parent process and see if that is the parent you're expecting. So like if you are delivering exe you're expecting someone to click on, well, check if the parent process is in Windows Explorer. If you are malware expecting to be executed from Internet Explorer, well, check if your parent is Internet Explorer. So that's not really rocket science either. This one is quite cool actually, self-debugging. What you do is you spawn a child, and the child is attaching a debugger to the parent. So when you're trying to attach a debugger to the parent, you can't because it's already being debugged. You can also use unhandled exception filter. Well, when you're causing an exception, you have your exception handler, you have the SEA chain, and you have the unhandled exception. When you're calling on the debugger, you're actually not getting an unhandled exception. So you detect that, well, my unhandled exception suddenly get handled. It has a drawback. It kills the process instead of continue executing it. But if you're doing an anti-reversing technique, I think it's quite okay anyway. Don't you agree?
That's what you want.
Yeah.
I mean, if you're a malware.
Yeah, if I'm up to the best stuff. I mean, this can you do for exploit creation or whatever. It's not just malware. For NtQueryObject, you have an object all types information class you can pass to it, which basically gives you a list of all the objects, and you can traverse it and traverse it until you find debug objects. It's a variant of the one I'm talking about earlier, but instead of looking directly, you traverse the list yourself because you don't trust in the system. So how do we protect against this one? Well, open process. Make sure that the debugger drops the SE-debug privilege. So you can't attach the analyzed software can't actually attach to privileged processes. And if you, for the parent, well, again, just fake it. Return the value you want it to have. So even if you are in only debug, make sure it gets what you're expecting, like Windows Explorer. For the parent, the parent is spawning a child that attaches a debugger. You can actually set the debug port in eProcess information to 0. And then you can attach another debugger. For unhandled exception filter, it's just making sure that the debugger is doing the right thing. It's not a quick fix on that one. For NtQueryObject, well, DL injection, fake the information. I mean, if the bad guys can do a DL injection, why can't we? So, anti-dumping. Dumping is when you let the malware load into RAM and you then dump the contents of the RAM, and suddenly you have an unencrypted, unpacked piece of malware, easier to deal with. There are a few funny or interesting or just waste of time techniques to deal with that. You have something like nanomites, where you're changing all the jump instructions in your code to the int3, which is calling the debugger. And you store all the original int3s, all the original jump instructions in an encrypted table. And then you're doing the spawning child, debugging the parent technique. And when you hit an int3 up, you're actually looking where you were, using that as input for actually find the correct instruction you remove from the code, put it back in, and let it go. I mean, it's not impossible to undo that technique. It's just time consuming until you find the key for this algorithm. And then you can just do it backwards and put it all back together. And if they really want to mess with you, they're putting a couple of int3s all over the code. that it just doesn't do anything. So is this breakpoint real or not? The stolen bytes is a variant of non-bytes, but instead of having an encrypted table on its own, it's actually using bits and pieces of code you already have in the binary or in the memory. So you actually don't have a separate piece of code that this is my lookup table. No. The binary itself is a lookup table. So it's very similar to return-oriented programming. If you understand what I mean. Then you can modify the PE header and change the size of image. If your tool is actually parsing this PE header and take that as the gospel, well, it's going to be painful. It has some drawbacks. Some tools or systems actually require it to be proper, but some better developed tools actually don't get the whole binary or crashes when using this technique. Then you have the whole virtual machine technique. And when I'm talking about virtual machine, I'm meaning like JVM, not like VirtualBox, not the whole hypervisor. I mean, you're having a bytecode that is executing, and you have a lot of dead code, a lot of red herrings. It's just doing a lot of extra work for what you actually want to do. All in the name for making it take longer to analyze. Because there is always a time limit on how much time you can afford to spend on a single sample. I mean, sure, if you're Stuxnet or Flame, you can spend a lot of time. But we are talking about somewhere between 50,000 and 200,000 variants daily. How much time do you think you get to analyze one single sample? And this tool, Thermida, is actually creating a unique virtual machine environment for every single sample. Think about self-modifying code. You get the idea? Yeah, God pages can also be used for just-in-time loading. So instead of detecting, oh, the debugger is present, I'm going to be nice, you can actually use it so, oh, you want to access this memory? Well, hold on, let me load it for you first. Okay, it's loaded. Now you can continue. Oh, you want this piece of memory? Hold on, let me unpack, encrypt it, load it for you, and you can continue. So if you wait until the malware is loaded and you want to grab the contents from RAM, you're only getting part of the malware, because parts of it is not even loaded yet. Or it can be loaded, but in encrypted form somewhere else in the memory. And you can always dump the allocations you no longer use as some performance penalty that, oh, you're on this part of the code. Okay, I don't need this one. I'm doing like a garbage collection. Remove that one. Oh, you need to access again. Okay, I'll load it again. So that's troublesome if you want to grab a complete image from the memory. Another cool thing I've seen is removing the P header from RAM. So you're losing all the relocations, imports, exports, all the nice information you want to have. You're just getting a piece of code, but you're seeing addresses. Jump here, go there, call this. What is that? Don't know. The operating system knows, but not by name, just by address. So that's also a way to bypass malware software, antiviruses, because okay, I'm looking for malware. Malware executable. Okay, scanning through memory through executables. Well, this is just a bunch of data. Let's continue. So, recap. Nanomites. Pain in the ass until you figure out what the key is. Because until you do, and you want to actually reverse it using the debugger, it's going to be painful. Stolen code or stolen bytes, same thing there. Is going to be painful until you find out the algorithm they have used to stash away the original code. Size of an image, that's a fairly easy one to bypass. You just need a tool that doesn't follow the RFC and just do. So you don't care about how large it says the binary is in memory. I don't care. I'm going to grab it all. Virtual machines, well, that's tough. I am not running virtual machines myself. I'm just letting them run in a dynamic analysis tool, which means let it run and see what it's actually doing. God pages, well, tough. You need to get it piece by piece. Time consuming, not impossible, time consuming. And removing the P header, it can be restored. Volatility is quite okay on that part, but can be problematic. Next technique there, exploiting the instructions. Is getting very debugger specific now. I have a couple of minutes left. The int2d is another interrupt instruction. And if you're having an OutputDebug connected to it, you're having an exception. If no debugger is present, and you do just your normal exception handling and continue. If the debugger present, you don't get an exception, and well, you don't do bad stuff. Stack segment. Now, when you're stepping through using a debugger, it's actually possible to fool it what it's going to be executing next. So you do a push and a pop SS, and when you're stepping through, if you're stepping through, you're actually getting straight away to the XOR. But if you're actually running the code, it doesn't move as well. Depending on the debugger. There's also a way to exploit the way the debugger is using prefixes. So again, you're using exception handling or no handling of an exception as a way to find out if you're being debugged. I've personally not seen this one myself. I just read about it. And recap. Interrupt 2D. Well, don't use only debug. or look out for that instruction and see. Normal code doesn't have debug interrupts enabled. For stack segmentation, same thing. Make sure you're using an up-to-date, patch, non-vulnerable debugger. If you find one, let me know. Same thing with instruction prefixes. So I'm doing a lot of dynamic analysis, which means I'm taking a piece of malware, I'm loading it up in my virtual box, and let it run and see what it's doing. And of course, the malware knows about this, so it tries to figure out if it's running in a hypervised environment. And does this while you're looking at the hardware, at the drivers, the operating system, and the serial number of the operating system. What add-ons do you have? And also doing VMI calls, the virtual machines infrastructure calls. Trying to talk directly to the hardware and see if it responds in expected ways. It also checks if there is an interactive environment. You know, if you are running 10,000 samples a week, you don't go around and touch every single sample yourself. So there's no keyboard input, no mouse input. I will trigger on that one. It's like, oh, no one has been using this computer since it's booted up, and yet I'm running. So, for hardware, make your virtual box or QEMU, whatever you're using, look as much as possible as real hardware. I'm cloning every single piece of computer I get my hands on when it comes to hardware specifications and BIOS and name of the graphics card and vendor and everything. When it comes to drivers, do not use the vendor supplied drivers. Use the Windows one. No need. Why hide that the hardware is VirtualBox or VMware if you're going to load the tools, the drivers for it, right? For operating OS version or serial, it's mostly for the public, well-known sandboxes, because that information is leaked, so you don't know exactly that, oh, you're in a Joe sandbox, or you're in a CW sandbox, or what it's called nowadays, GFI, whatever, or a known sandbox. Again, no drag and drop into the instrumented environment. Do not touch the virtual machine tools, not to guess the add-ons. For VMI calls, make sure you're using a hypervisor you actually can patch, so that's open source, so no VMware. Or you can use real hardware. That's the best way to avoid VM detection. Do not use a VM. When it comes to interactability, so make sure that the computer is faking as being used. No, move the mouse. Make sure that when the malware is asking how long time was it before since the mouse was clicked, it doesn't say 5 years ago. And when you're faking this interactivity, clicking buttons and so on, make sure you're not clicking buttons that doesn't actually exist or is not viewable. Because if you have an OK button that's 1 by 1 pixels, and the user actually managed to click on it, something is off. There's also a bunch of debugger-specific techniques. You can, using the find window call, and see if you're having an auto debug window or win debug window or any other popular debugger open, and see, oh, you're actually running auto debug. I'm not going to do anything right now. You have the OutputDebugString exploit for auto debug. If you're running dynamic analysis IDO using Cuckoo, you can actually the malware is actually checking if it's being DLL injected, and then behave differently. So how to fix that one? Well, change the name of the windows or patch the call, find window call, so it doesn't return those names. For the Cuckoo sandbox, run unhooked. You don't get as much information. That part is being worked on, but you lose some visibility to actually have it run more. Other techniques, just see, I have like 3 minutes left. Other techniques is junk code. Just put a bunch of code it's not going to use or doing nothing, like count the value of pi, and the anti-reverser is spending a lot of time looking at numbers of pi. Also, you have native code premonition. As you can do the same kind of code in many different ways, using different instructions, different flows. So the code can look a lot different, even if it's doing the same thing. No, there's no big quick fixes for that one. I'm running out of time, but I'm going to take some time here because I'm the last one for today. I have an announcement to make. Can you guess what it will be about? Zombie attack, someone said. Man in the middle. It's nothing that. Yeah.
You're getting married.
What?
You're getting married.
Oh no, I'm already married. No, I'm opening my malware archive, my malware zoo, to the public. I'm using a piece of software called VXCage that is available at vhk.malwareresearch.institute. Has a nice REST API where you can upload samples, download samples, search for samples. It's backed up by Amazon, so I'm using Amazon S3 and Amazon EC2 to run this one, which means the state of the hardware under the stairs in my house is not insequential. However, I don't want to have my site listed as a malware distribution point. So I'm actually going to require you to use credentials to log in. And how to get credentials? Very simple. You email me and ask for them. So you email me michael@michaelboman.org. You say this, I want to access your VXCage repository. I'm John Doe. I'm doing malware analysis as a hobby, or I'm doing it professionally, or I'm just interested in see what you're having. And you give useful contact information. So mostly it's kind of cyber stalk you. I mean, keep in touch. Like, oh, by the way, I'm planning to have a plan the downtime. I can mail it up to you. I can say, oh, we just got of a billionth sample, or the sample size is now 10 terabytes. No, 10 petabytes, right? Peta? Yep, whatever. Just so I can stalk and spam you. But that's me, not anyone else. If you want to have raw access to the archive, I mean direct access to the SQL database, direct access to the S3 object store, just email me at the address and say, hey, I would like to have raw access, direct access, and I can work something out. But if you say, oh, I want to download this 10,000 samples a week, okay. It's going to cost me more to charge you and actually get from do micropayments. But if you say, I want to access everything, we need to talk. As I said, just a quick intro. You have malware add, to upload malware. You have malware get and the SHA-256 checksum to download the malware. You have malware find to search for malware, and you can search by hashes, and there's the usual suspect: SHA-1, SHA-256, MD5, and SSDeep. I think you can search on CRC32 as well. I'm not sure. You can also search by date, like, oh, what samples was uploaded yesterday. You can also tag samples. So you can say, oh, this is a known malware family. I can tag it as such. All uploaded malware is being tagged by your username. So you can see who uploaded what.
Are you tagging it as well?
What?
Are you tagging it as well, so you put families together and stuff?
Yeah, I can do that. I'm not doing it at the moment. But I can add as many tags as I want. There's no limit. The docs and the source code is at my GitHub page. So you look there, you can duplicate it if you want. I don't know why, but if you think you can do it cheaper than I can, please go ahead. I mean, you have to start paying people to access it. Well, thank you. So you can cyberstalk me at mboman. My email address is michael@michaelboman.org, and soon is michael.boman@malwareresearch.institute. The malware repository is at vhcage.malwareresearch.institute. At the moment, it's just HTTP. HTTPS is done in about a week or so. I just need to get my mail sorted, apply for a certificate, and so on, but it's coming. And I also have a blog. It's very out of date at the moment because I'm being busy doing this. I mean, I can write about it, I can do it, I can't do both. So, thank you.